So today we're going to talk about thermochemistry, which deals with heat and chemistry, thermos meaning heat, and it's states of matter and energy that we're going to begin with. And you completed a lab in class today, and this is going to help cement some of those thoughts from that lab. So phases of matter. Phases of matter are solids, liquids, and gases. And if we look at them, solids are compacted together, liquids are a little further apart, and gases have the ability to move everywhere. And we're going to look at these specifically. We'll look at each of them individually. But they're increasing energy as we go from solid to liquid to gas. The temperature increases in order to change these states, and the attraction between the particles decrease. Now, for any substance, any element, any compound, we can have them in solid, liquid, or gas. Even though they're most common in certain states at room temperature, we can make them into any of the three phases. Solids have a definite volume and shape. We know what their volume is. We know what their shape is. The attraction between the molecules is high. They're held together tightly. And the ability for the molecules to move is very low. They vibrate, the atoms can vibrate in place, but we don't see any movement in any sort of solids. Liquids have a definite volume, but no definite shape. They take the shape of their container. So whatever they're poured in, that's what they take the shape of. The attraction between the molecules is medium. It's not as rigid as a solid, but it's certainly not as loose as a gas, so we say that it's medium. The ability for molecules to move is also medium. Again, they can take the shape of their container, but they can't just leave from each other. And then gases have no definite volume and no definite shape. The attraction between the molecules is very low. They're not attracted to one another because they're not being held together. And the ability for molecules to move is very high. The gas molecules move wherever they want. So these are the changes in phases, and a few of these are very common to you. You know that when you go from a solid to a gas, or solid to a liquid, it's melting. And if you take that same liquid and you heat it and you go to a gas, liquid to a gas, it's boiling. We also use the words fusion and vaporization. Fusion is this phase change here, vaporization is this phase change here. When we go the other way, when we go from a gas to a liquid, that's condensation, or from a liquid to a solid, that's freezing. It's easiest to think about this if you think of water. You think of water, well, you have ice. Ice melts into water. Water boils into steam. Steam condenses into water. Water freezes into ice. The two phases that aren't as common are from a solid to a gas, and that's sublimation, or from a gas to a solid, and that's deposition. Certain substances, iodine is one of them, goes directly from a solid to a gas, just choose to sublime. They skip that liquid phase. Dry ice is another one that does that. Solid carbon dioxide goes straight to a gas. So this is one of the most important diagrams of this chapter, and this is what we worked on in lab today. It's a heating and cooling curve. And it shows the temperature and energy from a substance over time as it changes from a solid to a gas. You definitely would like to have this in your notes. You will have to label one of these at some point. So what it's showing us is that here's temperature increasing, and here's the heat energy. So we can think of this, and we can use water as our analogy, that here we have ice. Okay, so we have our solid, and we're heating it, so we're warming our ice, and our ice is melting. And if we notice the temperature, the solid ice, it's frozen, and it's increasing, and if this is ice, this point here is 0 degrees Celsius. Okay, 0 degrees Celsius is where ice melts, or where ice freezes. That temperature will remain constant until all of that ice has turned into a liquid. Then we have our liquid water. Then once it's all water, we're going to heat that liquid water until it starts to boil. That temperature will remain at 100 degrees Celsius until all of that liquid has turned into a gas, in which case we can then heat the gas more and more if we have it contained. The opposite is true. If we have the gas and we cool it, it condenses at 100 degrees. It will stay at 100 degrees till it's all liquid. It will then cool until we get to 0 degrees Celsius, where we'll stay constant with that until it's all frozen, and then we can decrease the temperature. So this idea, these plateaus are very, very important. This is a new thing. This, although we used ice for this shape of this graph is true for any substance. They all follow this exact same graph. And that's what is an important factor in this unit. So another very, very, very important definition in this unit is the definition for temperature. Temperature is a measure of the average kinetic energy of the particle. So kinetic energy is the energy of motion. You learned that in physics. And temperature is just a way that we measure the average kinetic energy of the particles, okay? Because we're measuring that energy, so we're measuring that kinetic energy. The lower, the less kinetic energy, the cooler it is, the more kinetic energy, the faster those particles are moving. Heat is the flow of energy from one object to another. So when we refer to things as heat is the energy that's flowing from a warmer object to a cooler object. As we add heat energy, the kinetic energy of the particles increase and the temperature increases. In solids and liquids and gases, as the average kinetic energy of the particles changes, the temperature changes. So change in, we know the symbol to be change in kinetic energy is equal to a change in temperature. And we'll be measuring a lot of changes in temperature in this unit. So looking at phase changes, specifically melting point, added heat energy allows the particles to move around and overcome their intermolecular attraction. So we continue to add heat to that ice, and it's allowing those particles to move around, overcome their attraction to each other, and turn into a liquid. As molecules move away from each other, the solid becomes a liquid, and there is no temperature change until all of the solid changes to a liquid. That's the flat part on the graph that you drew. So there's no temperature change. The freezing point, heat is lost and attractive forces pull the molecules closer together to form solid. There's also no temperature change until all of the liquid changes to a solid. That flat part of the graph is very important. And I've pointed it out not only in the graph, but then again in this slide, that this idea that there's this plateau during melting point and freezing point. Heat energy during the melting phase is being used to overcome attractive forces between the molecules. In solid phase, the molecules stay in place and vibrate. In liquid phase, the molecules can flow past each other. With a phase change, there is a change in the potential energy, the energy of position of the molecules next to each other. And so because we're adding energy, we know we're not increasing the kinetic energy at that point, there has to be a change in the potential energy during those plateaus on the graph. Melting point and freezing point are at the same temperature. Another key point. People don't tend to think about that we think about water freezing at 0 degrees Celsius, but water melts at 0 degrees Celsius. We think of water boiling at 100 degrees Celsius, but water also condenses at 100 degrees Celsius. So when it's melting, the potential energy is increasing. When it's freezing, the potential energy is decreasing. Boiling point and condensation point are the same temperature. Same thing as boiling, potential energy is increasing. Condensation, potential energy is decreasing. Each substance has its own characteristic melting and freezing point. So we've been referring to water, so we've been referring to 0 degrees and 100 degrees, but every substance has its own set of points. It has its own characteristic melting point, its own characteristic freezing point, and the same with boiling point. We can identify substances by knowing their melting point or freezing point or boiling point. Many times things are checked by boiling and see what temperature it boils at, and that determines what the substance is. So it says here to identify each phase and identify the type, kinetic energy, potential energy for the sections. So looking at A, C, and E, if A is here, A is going to be a solid, C is going to be a liquid, and E is going to be a gas. At this point, even though it didn't say to do it, we're going from a solid to a liquid. So here we have melting, and here we have boiling. And if we're looking at our energy changes, solid, we're dealing with kinetic energy increasing. Liquid, here we're dealing with kinetic energy increasing. Gas, we're dealing with kinetic energy increasing because we're moving our way up the graph. It's not a cooling graph. And then how much heat is needed to raise the temperature in a solid, liquid, or gas? So how much heat do we need? Well, there's some factors that contribute to that. The amount of heat that's needed depends on, one, how much substance you have. If you're heating a teacup of water versus heating a pool's worth of water, it's going to take a lot more energy to warm that pool up than it is to warm up your cup of tea water. How much do you want to change the temperature? Do you want to change the temperature 10 degrees? Do you want to change it 30 degrees? Do you want to change it 100 degrees? How much you want to change the temperature also factors into how much heat you need. And then 3, the substance itself. Different substances take different amounts of energy to heat them, to heat their amount. Water happens to have what's referred to as a high heat capacity, and we're going to learn a lot about that as we move into it. So we will move into the calculations portion of this tomorrow, but for now you have a good background on heat and phase changes.